In 2007, a fossil collector and paleontologist named Marcus Poschmann was working a quarry near the town of Prüm in the Rhineland region of Western Germany, when he found something that, on its own, doesn't sound like much. A single claw, not attached to a body, not part of a connected skeleton, just one isolated chelicera, the pincer-like grasping appendage that sits at the front of a Eurypterid's head. Except this claw, even incomplete, measured 36.4 centimeters long, and the missing piece at its tip meant the whole structure would originally have stretched to somewhere around 45.5 centimeters, the better part of 1.5 feet, on a single claw, from a single animal. Poschmann brought the find to paleontologists Simon Brady and Eric Tetley, and the three of them did something you can actually do with a fossil this fragmentary, provided you have enough related, more complete specimens to compare it against. Eurypterids like this one have a fairly consistent, well-documented ratio between claw length and total body length, across close relatives, where we do have the full animal preserved. Close cousins like Pterygotus and Achitheramus, where both the chelicera and the rest of the body survive together in the same specimen. That ratio is exactly the kind of tool paleontologists reach for constantly when a spectacular piece of a fossil turns up, without the rest of it attached, checking it against several related species rather than just one, to make sure the resulting estimate isn't riding on a single lucky comparison. Run this claw's measurements through that ratio, and the number that comes out the other side is a body length of approximately 2.5 meters. A sea scorpion, the length of a tall adult human, built almost entirely around a single weapon, roughly 1.5 feet long, a claw alone that would reach from a grown adult's fingertips past their elbow. Brady, Poschmann, and Tetley published the finding in the journal Biology Letters in November of 2007 under a title that wasted no time getting to the point. Giant claw reveals the largest ever arthropod. Isolated chelicerae this size essentially never turn up intact. Eurypterid claws are thin-walled, articulated structures built for speed and grip rather than durability, and the odds of one surviving fossilization at all, let alone surviving it at more than 1/3 of a meter long, are low enough that a find like this tends to get treated as a once-in-a-career event for the paleontologists involved. Poschmann had spent years working Devonian sites in the Rhineland by that point, and this was still the discovery that ended up defining the animal to the rest of the world, and for 14 years that title held. Then, in 2021, a different animal entirely challenged it, and the story of exactly how close that challenge actually is turns out to be worth telling properly, rather than glossing over. We'll get there. But to understand what's actually being compared, and why this specific claw matters as much as it does, we need to back up much further than 2007, because this animal had already been named, misidentified, renamed, and quietly sitting in the scientific record for close to a century before anyone found the fossil that made it famous. The animal's story on paper starts in 1914, when German paleontologist Otto Jaekel described an isolated fossil fragment, Ea pretelsen, essentially the segment of a Eurypterid's body sitting just before its tail spine, that had turned up at a site called Alken, also in the Rhineland, in rock dated to the early Devonian. Jaekel compared it to other known material and concluded he was looking at a species of Pterygotus, an already established genus of large predatory Eurypterid, and named it Pterygotus rhenanii, after the Rhineland region where it was found. Working only from that single fragment, Jaekel estimated the living animal at around 1 meter long, maybe 1.5 meters if you included the claws. A big animal for a Eurypterid, not yet a record breaker. Nobody had any reason to think otherwise, because nobody had much more than that one pretelsen to go on. More material started turning up over the following decades. In 1936, Norwegian paleontologist Leif Sturmer published a considerably more detailed description of the species, working from additional fossils, including genital appendages, chelicerae, and fragments of the metastoma, a large plate on the underside of the abdomen, recovered by German paleontologist Walter Gross near the town of Overath. That expanded picture let researchers refine what this animal actually looked like, but it was still classified as a species of Pterygotus, one large Eurypterid among several. That changed in 1964 when British paleontologist Charles Waterston took a closer look at the accumulating anatomical evidence and concluded that this species didn't really belong in Pterygotus at all. The abdominal appendages were segmented, structurally distinct from the equivalent structures in true Pterygotus species, distinct enough, in Waterston's judgment, to justify splitting it into its own genus entirely. He named that genus Jaekelopterus, honoring Otto Jaekel, the same researcher who described the original fragment 50 years earlier without ever seeing anywhere near the full picture. So by the time Poschmann found that 45-centimeter claw in a German quarry in 2007, Jaekelopterus rhenaniae had already been a recognized, named species for over 4 decades, quietly filed away as a large, but not exceptional, early Devonian predator. What that single claw did wasn't discover a new animal. It revealed that the animal science already knew about had been dramatically undersold the entire time, by a wide enough margin to make it, at least for the next 14 years, the largest arthropod confirmed to have ever existed on this planet. Full stop. Bigger than any living crab, any living spider, any other fossil arthropod anyone had measured before it. Now, what does a 2.5-meter predatory claw actually let you infer about how this animal lived, beyond just how big it was? Quite a lot, as it turns out, because the shape of a chelicera isn't neutral. It's built for a specific job. Jaekelopterus's claws are enlarged and robust, with a curved free ramus, the movable pincer segment, and rows of denticles, small tooth-like projections, of noticeably different sizes running along the gripping surface. That combination, a curved hook shape paired with irregular denticles, shows up today in modern scorpions and predatory crustaceans that use their claws for strong grasping and puncturing, rather than the more delicate, slicing or filtering setups you see in some other arthropod lineages. Researchers studying the anatomy in detail have concluded these chelicerae were most likely built for grasping, with the robustness of the structure suggesting they could plausibly have handled some degree of crushing and puncturing as well, not just holding prey in place, but actually damaging it on contact. Pair that with the animal's compound eyes, which show a level of visual acuity comparable to genuinely active modern predatory arthropods, rather than the duller, lower-resolution vision you'd expect from a scavenger or an ambush specialist working mostly on touch and vibration, and you get a consistent picture. Sharp eyesight built for tracking prey, plus grasping, puncturing claws built for holding and damaging whatever it caught. Jaekelopterus wasn't just large. Every available piece of anatomical evidence points toward an animal actively built to be the apex predator of wherever it lived. Here's a detail that tends to surprise people, given the popular nickname this whole family of animals carries. Eurypterids get called sea scorpions constantly, and it's an understandable shorthand, since the body plan does superficially resemble a scorpion's, and plenty of Eurypterid species genuinely were marine. But the rock formations where Jaekelopterus rhenaniae specimens have actually been recovered, in the Rhineland region of Germany, tell a different story about where this particular animal spent its life. Those deposits represent brackish to freshwater conditions, not open ocean, closer to river deltas, estuaries, and marginal environments where freshwater and seawater mixed, than to anything resembling deep sea. A related species, Jaekelopterus howelli, turns up in similar estuarine strata in Wyoming, in the United States, reinforcing the same pattern. So picture this animal not patrolling open water like the name suggests, but working the murkier, resource-rich margins where rivers met ancient seas, the early Devonian equivalent of a river delta ecosystem, hunting through water that was probably cloudy, shallow, and thick with other life competing for the same space. It's a genuinely strange picture once it sinks in. Not a monster cruising some vast, open Devonian ocean, the way the sea scorpion name practically demands you imagine it, but something closer to a 2.5-meter ambush predator working the shallows of a muddy river mouth, in water you could plausibly have waded into up to your knees before ever noticing it was there. And what was it hunting? The fossil evidence for that is genuinely direct, not just inferred from anatomy. In deposits associated with Jaekelopterus howelli, researchers have found fossils of an early jawless fish called Lecreaspis patella, bearing puncture wounds consistent with an attack from exactly this kind of large pterygoid claw. Combine that with the broader ecological picture, an apex predator sharing its estuarine habitat with early jawed and jawless fish, other Eurypterids, and quite possibly members of its own species. And the working consensus is that Jaekelopterus fed on early vertebrates and smaller arthropods, very possibly including its own kind when the opportunity presented itself. It's also worth sitting with the broader picture this connects to. This was an era when Eurypterids and early fish were locked in what researchers describe as an evolutionary arms race, with the fish gradually developing thicker, bony armor and stronger jaws, partly in response to predation pressure from animals exactly like this one. The early jawless fish sharing these estuaries, agnathons covered in bony plates rather than scales, and the early jawed fish that were just starting to diversify alongside them, weren't armored like that for no reason. A 2.5-meter Eurypterid with crushing, puncturing claws is exactly the kind of predator that makes heavier plating a worthwhile investment, generation after generation. Jaekelopterus wasn't hunting in an empty landscape. It was one active, escalating pressure in a broader contest that was actively reshaping the vertebrate lineage that would eventually include us, long before any of those fish had jaws sophisticated enough to bite back with much confidence. But here's where the story gets more interesting than just biggest claw, sharpest eyes, scariest predator, because it turns out that description doesn't apply evenly across this entire family of giant Eurypterids, even though popular coverage tends to lump them all together. A 2015 study published in Biology Letters, led by Victoria McCoy alongside James Lamsdell, Marcus Poshman himself, Ross Anderson, and Derek Briggs, took a comparative look at the eyes and claws across several genera in this pterygoid group, including Jaekelopterus, Pterygotus, Eurypterid, and a genus called Achypteramus, plus a closely related sister genus, Slimonia. What they found complicated the assumption that all of these giant Eurypterids were simply interchangeable apex predators at different sizes. The visual acuity part of that comparison isn't guesswork either. Compound eyes like these are made up of individual lens facets, and the number and spacing of those facets, visible directly on well-preserved fossil eyes, translates fairly reliably into how sharp an animal's vision actually was. The same basic logic used to compare visual resolution across living insects and crustaceans today. Achypteramus, despite being a genuinely large pterygoid in its own right, turned out to have comparatively weak slicing-style chelicerae and a visual system with noticeably lower acuity than the others, a combination that reads much more like a generalist or even scavenging lifestyle than an active hunter chasing down fast-moving prey. Jaekelopterus and Pterygotus, by contrast, both showed the robust, crushing-capable claws and the sharp, high-resolution vision consistent with modern active predatory arthropods. So the honest, more precise version of the apex predator claim isn't that all giant sea scorpions earn that label automatically by virtue of being enormous. It's that Jaekelopterus specifically earned it on real, testable anatomical grounds, while at least one of its equally giant relatives was very plausibly living an entirely different kind of life nearby. Which raises the obvious next question, the one that's actually harder to answer with any confidence than you'd expect. Why did any of these animals get this large in the first place? For a long time, the default explanation for Paleozoic arthropod gigantism, whether we're talking about giant dragonflies, giant millipedes, or giant sea scorpions, leaned heavily on elevated atmospheric oxygen levels, sometimes estimated as high as 30% compared to today's roughly 21%, on the logic that modern arthropods are size-limited, partly by how inefficiently their respiratory systems deliver oxygen as body size scales up. So more oxygen in the air should mean arthropods can grow larger before hitting that ceiling. It's a tidy explanation, and it shows up constantly in popular science coverage of this era. But a 2024 study published in Proceedings of the Royal Society B, led by researchers including Rubenstahl, Mongardino-Koch, Lamsdell, and Briggs, built a detailed evolutionary tree covering the majority of known Eurypterid species, specifically to test whether oxygen, temperature, habitat, or diversity actually correlated with when and where gigantism showed up across the group's history. The result complicates the tidy version considerably. The The study found that Eurypterids evolved gigantism independently at least 9 separate times across their family tree, and found no compelling evidence that elevated oxygen or temperature actually drove those events, nor any consistent link to habitat type or local competition. What the data pointed toward instead was that giant size tended to appear in short, rapid evolutionary bursts, and that whatever was driving those bursts looked more like intrinsic factors within specific lineages than any single external environmental trigger, applying uniformly across the group. In plain terms, the honest current answer to why Jaekelopterus and its relatives got this big isn't oxygen, or at least not simply oxygen, and it isn't yet a fully solved question at all. It happened repeatedly, independently, for reasons that still aren't completely pinned down. Now, back to that record I mentioned at the very start, because this is where the story actually catches up to the present. For 14 years after that 2007 paper, Jaekelopterus rhenanii held the title of largest arthropod ever confirmed to have existed. Full stop, no real competition. That changed in 2021, when a team studying a fossil discovered back in 2018 on a beach at Howick Bay in Northumberland, England, published a comprehensive redescription of a giant carboniferous millipede called Arthropods in the Journal of the Geological Society. Their analysis put that specimen's length at somewhere between 1.9 and 2.63 meters, with an estimated body mass of around 50 kilograms. Compare that range against Jaekelopterus's estimated 2.33 to 2.59 meters, and what you get isn't a clean changing of the guard. It's closer to a photo finish, 2 estimated ranges that overlap almost entirely, from 2 completely different lineages, evolving gigantism independently, roughly 90 million years apart. Depending on which specific specimen you're measuring and which reconstruction method you trust most, either animal could reasonably be called the largest arthropod that ever lived, and a fair amount of current popular coverage, understandably, still defaults to whichever one it happened to write about most recently. The honest answer, as of right now, is that it's genuinely too close to call with total confidence, and that's not a disappointing outcome. It just means the actual record for largest arthropod in Earth's history currently belongs to 2 wildly different animals, a giant land-dwelling detritivore and a giant estuarine predator, separated by tens of millions of years, both landing in almost exactly the same size range, for reasons that circle right back to that same unresolved gigantism question. There's one more piece to this, and it's recent enough that it genuinely wasn't part of the story, even a couple of years ago. In 2025, paleontologist James Lamsdell re-examined a species originally named Pterygotus marilandicus, described all the way back in 1964 by Erik Kjellesvig Waring, based on a fragmentary, fairly unimpressive telson, the tailspine segment, recovered from Silurian age rock in the Mackenzie Formation in Maryland. Lamsdell's reassessment found that this telson's shape, specifically a broad, flattened posterior margin and a clearly triangular outline, matched features characteristic of Jaekelopterus and not found in any other pterygodid genus. Based on that, he transferred the species into Jaekelopterus, renaming it Jaekelopterus marilandicus. That reclassification matters for a reason that goes beyond simple bookkeeping. Every other known Jaekelopterus species, Rhenanii from Germany, Howelli from Wyoming, comes from Devonian rock. Marilandicus comes from the Silurian, the geological period immediately before the Devonian, meaning this species is substantially older than either of its more famous relatives. Eurypterids as a whole stretch back further still, with the earliest members of the group appearing somewhere around 460 million years ago. So this reclassification doesn't rewrite when Eurypterids began. But it does rewrite when the specific giant claw-producing lineage began, and moves that starting point measurably closer to the group's origins than anyone had previously placed it. As of 2025, Jaekelopterus marilandicus is the oldest confirmed species in the entire genus, pushing the documented history of this lineage backward by millions of years, and quietly confirming that the animal responsible for the single most famous claw in Eurypterid history had relatives establishing the family name long before that specific 2.5-meter predator was patrolling German river deltas at all. So here's where this genus actually stands, once you put the whole thing together properly instead of stopping at the headline. A fragment of tail found in 1914 got misidentified into the wrong genus entirely. 50 years of additional fossils slowly built out a fuller picture until a British paleontologist decided the animal deserved its own name in 1964. Then, in 2007, a single 45-centimeter claw found by one collector in one German quarry revealed that this already named, already studied animal had been quietly undersold its entire scientific existence, briefly making it the single largest arthropod confirmed to have ever lived on Earth. A title it may still hold, or may currently share, with an unrelated giant millipede discovered on a beach in England 14 years later, depending on whose reconstruction you trust. And in 2025, a piece of Silurian tail fossil sitting in the record since 1964 quietly got reassigned into the same genus, pushing the whole lineage's known history backward by millions of years. This is a species that has been actively rewritten roughly once every 15 to 20 years since it was first described, and there's no particular reason to think 2025 was the last time that happens. So, the largest arthropod ever confirmed to exist, or one of exactly two candidates for that title depending on the week, was built almost entirely out of scraps. One tail fragment, one detailed follow-up specimen, one genus-defining reclassification, and one claw so large it rewrote the whole animal's reputation on its own. Not bad for an animal whose entire fame rests on pieces nobody ever found attached to each other. It's a fitting close to this two-part detour into prehistoric arthropods, honestly. Last time, a giant fossil spent 25 years locked in a bank vault before anyone could prove it wasn't actually a spider at all. This time, a single claw sat in a quarry near Prüm for who knows how many millions of years before one collector happened to dig in exactly the right spot. And both stories end the same way, with a record quietly changing hands the moment somebody finally got a proper look at the evidence. Alright, that closes out the arthropod side of things for now, so next time, we're heading back to the dinosaurs. And specifically to a discovery that didn't just reveal one new animal, it completely rewrote what scientists thought dinosaurs even were. In 1964, in Montana, a paleontologist named John Ostrom found the remains of a fast, active predator called Deinonychus. And the animal's anatomy was so at odds with the sluggish, cold-blooded picture of dinosaurs everyone had accepted for decades that it single-handedly kicked off what's now called the dinosaur renaissance. That's next, and there's a genuinely contested piece of that story too, about whether this animal actually hunted in coordinated packs the way it's usually shown, that we'll get into properly. Let me know in the comments what you want cataloged after that, and subscribe to Claw Catalog so you're here for it.